So lesson 1 of electricity, and we're starting with static electricity, and lesson 1 is Coulomb's law. And what we're interested in here is the force between two charges. So first let's recap. We remember there's two types of charges, plus and minus. Okay, and we know that like charges repel and unlike charges attract. Okay, like charges repel, unlike charges attract. Okay, so if you have two plus charges, they repel. If you have two minus charges, they repel. Plus and a minus charge, either way, they attract. So I think we're happy with all of that. We don't need to know anything else about what the charges are. This is our model. We have two types of charges, plus charges and minus charges. We also have the idea of neutral, in that if there is an equal number of plus and minus charges on a body, let's say me, okay, that means I'm neutral, okay, overall neutral. So if I have 40,000 million plus charges and 40,000 million negative charges, I'm neutral, okay. So that's where we're at the moment, okay. And this idea of like charges repel and unlike charges attract, we have a very simple experiment, which we will now try to do, okay. Forgot to bring home a retard stand, so we're improvising. Okay, so what we have is, if you look at this, okay, so I have a perspex rod. Okay, so the perspex rod, I'm charging the perspex rod, okay, in a wool hat that has no other use at the minute, okay, right, and I'm putting it in to the stirrup, as we call it. Okay, try to get it to balance in the stirrup. Okay, balance in the stirrup. Now I'm going to charge another perspex rod. Now if you charge a perspex rod, what happens is the negative charges repel, the negative charges excess on the perspex rod rub off onto the wool. The wool attracts the perspex charges more. Okay, so what should happen is these charges should repel. So at the moment it's pretty stopped. If I bring this towards it, off it goes. It repels. Okay, I can get it to go quickly. Look at it, okay. I can try to get it to stop and go the other way. Right, there it goes. Okay, right. So now leaving this alone. Okay, that's your perspex positively charged. Okay, I'm not going to get my polythene rod. I'm going to rub it again in the wool. Okay, traditionally it was silk, but I'm afraid no silk hats here. Okay, right, and now these should attract. So it's going that way, so I'm going to try to get it to come back. Here it goes, it's attracted. Okay, and get it to go faster. Okay, so they're attracting. Right. So all the charges attract. And I suppose what we should do, just to show, okay, these are polythene. Now the polythene, the electrons in the polythene are excess. So basically, when you're rubbing with the wool, in this case, the polythene takes the electrons, so it becomes negatively charged. Okay, I'm going to try to get that to together. And if I charge the other polythene, now these should repel. Okay, so it's going that way, so I'm going to try to stop it. Get it to go the other way. There it goes. Something for you to do when we return to 4C sometime. Okay, so that's it. Right, so it's in the notes. Very straightforward. Doing a sort of experiment, you may well have done it at the time. So we have the direction. Okay, if we know there's force between charges. If they're like charges, they repel. If they're unlike charges, they attract. Okay, perspex. Okay, X at the end of perspex, twisted around, is positive. So perspex gets positively charged, it loses electrons to the wool. Okay, the electrons being the negative charges. Okay, and polythene, okay, like a polythene bag, okay, it takes the electrons in the wool, so that's negative. So polythene, negative. Okay, think of E at the end being electron, negative. You see, so X at the end is plus, E at the end is negative. Right, okay, the next thing we're going to look now is the force. What's the magnitude of the force? Okay, so remember from our mechanics back along, the magnitude of the force was the size of the force. So we want to see what the relationship, like, in other words, if the forces are bigger, if the charges are bigger, what happens, okay? So charge is measured in a thing called coulombs. Okay, charge is measured in coulombs. And it's named after a guy called Charles Coulomb, okay, and there's a law called Coulomb's law, right? And this is basically the core of what we're looking at today, okay? So let's think about it, okay? Now we're talking about electricity, but I'm going to use geomags again, okay? Now there is a link between electricity and magnetism, but I'm not worried about that today, okay? So if I have two plus charges, let's say two charges of +1, here they are, okay? And I put them at a certain distance apart. Unless they're both plus charges, there will be a repulsion. Now, think about it. If I take another two plus charges, okay, or if I take the same original plus charge, this one here, and I get another plus charge of the same size and put it near it, again, if I put them in exactly the same distance, again, the charge will be +1. Okay, the force between them will be, we call it +1. But what happens if I put two of the charge on one side? So effectively, that's like this. Like this is getting a force of 1 from this, a force of 1 to this. So the total force is 2. Okay, the force is 2. It's doubled. Okay, and if I put 2 on this side, the total force will be 4, and so on and so on and so on. We'll come back to that again later. But let's look at it. What we're basically saying is we have two objects charged, let's say Q1 and Q2. Okay, they're both objects charged at Q1 and Q2, right? And we want to find the force between them, okay? And we have said the force is proportional to charge 1, and the force is proportional to charge 2. And in fact, we've said the force is proportional to Q1 multiplied by Q2, okay? So if there's a force of 3, if there's a charge of 3 on one side and 2 on the other side, it's effectively force, a 6 force, okay, force of 6, right? So that's what we've done. Remember, this proportional, okay, it multiplies by a constant, right? What about the distance? Now this is where things get interesting, and we get onto a thing called the inverse square law. If you think about it, okay, and if I take two examples here, okay, so if I take a ball like that, okay, that size, right? Now think if the charge is in the middle, in the center of the ball, okay? And at this point, if you're this far away from the center, okay, so the radius away from it, okay, if you're the radius away, there'll be a certain force. But the charge is having an effect over an area, the area of the ball. Okay, what if you go out further? Okay, what if you go out? Okay, so it's the same charge is in the middle, but you're now gone further away. Okay, so the radius has increased. Okay, will the force be smaller or greater? Well, it should make sense that the force will be greater when you're closer to it, okay? And the force will be smaller when you're further away from the center, okay? So this would be the greater force will be at this radius, the radius of the table tennis ball, and there'll be a smaller force at the radius of the football. This is the size for football, right? Now, but it depends on the area, okay? So basically, what we say is that as the area goes up, the force goes down, and it's an inverse relationship. So the force is proportional to 1 over the area, okay? But you all know, of course, that the area of a sphere from your maths in room 2D or 5B or however you do it is 4 pi d squared. Okay, it's proportional to 4 pi d squared. Okay, that's the area of where d is the distance from the charge. Okay, d is the distance from this charge of the radius. Okay, so I'm using d for distance. You could use r if you like, but we generally use d. So distance from the center to the outside of the ball. That's it. So in this case, okay, so that would be d. Right? So the force experienced, if you put the charge here, it is proportional to the area, but the area is 4 pi d squared. So this, okay, we can put these together, right? Now, let's get clear, this is not a proof, okay, we're just trying to step it through, but we're trying to see where there's a logic to this this formula that we're going to be using in a bit of a paper. Okay, so we end up with this formula, F is proportional to Q1, Q2 over 1 over 4 pi d squared. Okay, so it's proportional to the product of their charges and inversely proportional to the area of the circle, or because 4 and pi are constants, we can ignore those for the time being, and it's inversely proportional to the distance squared. This is what's called an inverse square law. So when we get an inverse square law, it's to do with the inverse square comes from the area of the sphere. Okay, Right, so we have this. Now to get rid of that we need a constant, okay, and for reasons that are historical, okay, the constant is put underneath rather than on top, and it's called epsilon, Greek letter epsilon. It's called the permittivity, and we end up with this formula. Okay, so the constant is the permittivity. Okay, right, and that's the law. That's Coulomb's law. Okay, so let's go through the steps again. Okay, F is the force between the charges. Q1 and Q2 are the size of the charges. Okay, so the force proportional to the product of those, and it's inversely proportional to the distance between them. The distance between them. Inversely proportional to the distance between them. So the reason we've gone through this on the board is that you see that there's a logic to it. Okay, you don't have to be able to rehash this, okay, because we're just going to be using this, but I don't want this formula to come from nowhere, okay. But what's very important is it's an inverse square law, okay, force proportional to 1 over d squared. Think about it. As d gets bigger and bigger and bigger, the distance away from the charge, the force gets smaller and smaller and smaller, but technically never goes to zero. And let's go back to our atom, and we spoke about the electromagnetic force, and this is the law for the electromagnetic force, the force between charges, and we said it had infinite range because it obeyed the inverse square law. That's the inverse square law. You've seen it for the first time now, and you're getting an idea of it. Let's just recap very briefly, because with all the props that we have, okay, think about it. The charge is the center of the ball. At the surface of the ball here, the force will be at a certain value. If you go out further, the force will be smaller because the distance will be larger, and the distance from the center is the radius. When you go out further, it's going to be larger again, and when you go out further, it's going to be even larger. Okay, that's it. Thanks a minute.